Well, I should thank Tamara Grava, who is holder of the Morlet chair, and so therefore that's why we're all here. Also, I should thank the organizers as well. Thank you very much. So let me go back in time a bit, and so the work that I'm going to talk about is joint work with Mark Adler from Brandeis University and Kurt Johansson from KTH, some of it with K and some of it with Mark Adler. So let me talk about two things. I will talk about rectangular Aztec diamonds, domino tilings of rectangular Aztec diamonds. I will explain to you what it is. And also, towards the end, I will say something about lozenge tilings of non-convex polygons. So, as I say, let me go back in time a little bit. That is called an Aztec diamond, okay? And so you want to tile that with dominoes in a certain way. There are many questions that you can ask about that. And what we are interested in mainly is what happens when this becomes very large. Because then that's where you see certain phenomena that you might not expect, I mean, intuitively. So you are, yes, now let me, of course, there are four kinds of dominoes. It can be horizontal, it can be black on the left, blue on the left, and blue on the right, and it can be vertical, blue on top and blue below. There's a way you can assign colors to them. You don't have to, but let me immediately say something about the height function. These tiles are equipped with a height function. And that is to say that if this is height h, say 0, 0, 0, then this will be height 1, 1, 1, okay? So you might say it is it's like a domino which is slightly tilted. It's 0 here and it would be 1 here. And this one is, this vertical one is different. This is h. Say this is 0, 0, 0 here and 1, 1 and 1 there. This is flat. It's horizontal, which is flat, and then this one is different. I mean, it's somehow the mirror image of that. This will be 0, 0, 0, and then this will be 1, 1, and 1. This is the height function. And it makes sense to draw actually to draw a level line, which will be sitting at h plus a half. So if this is 0 and this is 1, this will be sitting at 1/2. I draw a level line which goes from 1/2 to 1/2 here, okay? And I can arrange things in such a way that it's a straight segment. I mean, that doesn't matter. And the same with this, you see, this will be 0 and 1, so this is height 1/2, and this will be height 1/2. I draw that level line. These dots, I will say something about that later on. And the same thing here. Here there's no level line because it's not 1/2, okay? The level lines are always at 1/2, 3/2, 5/2, etc. Okay? So the same thing you can do. You can do lozenge tiling for hexagonal regions, and you can also, there are three kinds of tiles. You can give them colors. You can also give them heights, etc., etc. But I will come back to that later on. So these are the prototype pictures of what you get for large Aztec diamonds. Okay. So what you see, these pictures were produced by Sunil Shita, who is now at the University of Durham. So this has 100. So there are 100 squares on the side. And if you do that simulation, you get, in fact, that this is frozen yellow, this is frozen blue, this is frozen green, and then you get some sort of shape like this, okay, shape like this, and then inside it's shown to be, people have shown this is a Gaussian free field. We know absolutely almost everything about it. We know that on the side here, this is the Airy process, which is a stationary process, which is at every point, the distribution is like Tracy Whittem. And then also we know the distribution along that boundary here, and that's the so-called GUE minor process. Now, this is a picture where the horizontal tiles are more probable than the vertical ones. So you take A to half. You will see precisely what it is in a moment. So then you get, instead of an Arctic circle, you get an Arctic ellipse, okay? So, but I'm interested in I'm actually interested in a different model. And I will explain you why. I mean, it's not just because if I want to generalize, I will explain you why later on, okay? So I look at a different model, which is the following. It's a sort of rectangular model, but you see that here there's a little indentation, and then I go on. So this is white, 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 white. Then I have this little indentation. You might say a non-convexity. And then it goes on black and black. Blue and blue, I should say. And the same, symmetrically, you do the same thing here. And I will call these quantities will come up over and over again. This will be n, as before. I mean, the number of blue squares on that side. And then we have m1 here, which is n plus a certain number kappa. In this case, the kappa is 2. And this is called m2, okay? And so it's the same message as before. We are interested in knowing what happens when the n becomes large, the m1 becomes large, the m2 becomes large, but where kappa remains finite, okay? That's what we are interested in. So, I mean, you tile this with the same tile that I've shown you before, and I immediately want to show you some simulation, because that's really tells you where we are going to. So this is also simulation by Sunil Shita. This is a situation where n is 100. So that's to say there are 100 squares here and 100 squares here. The kappa is 0, that's to say that this length is equal to that length. And well, I have to explain you later what rho and r. We'll come back to that picture later on. You see there's a little difference between this line and that line. So this is frozen blue. This is frozen yellow, frozen red, and there's a boundary between the two, and the same here, the boundary between the two, but it is slightly off. And then you have the same thing here, same thing here, same thing there. So you get sort of two Arctic circles, but there's something going on in the middle. There's something going on in the middle, and that's why I'm interested. That's exactly what I'm interested in. Yes. Say it once again.
In the previous slide, you are only two colors.
Two?
Two colors.
Yes.
And now four.
No. Before there were. Let's see. I mean, did I? No. Here there are also four colors. There are also four colors. Mm-hmm. Yeah. I mean, it's horizontal with blue on the left, horizontal with blue on the right, vertical with blue on top, and blue below. So you have four different situations, okay? So, so here too you have this, and as I say, we are interested in what happens here, okay? Now you might say, why look at that, and that will become clear later on. But so most of my talk will be trying to figure out what the probabilities are in between here, what's really going on, okay? Yes. So I have to, well, the first question, such a rectangular Aztec diamond, is it tileable? Because you may start doing it and it may not work in the end. Okay, but there's indeed a very precise condition. It's tileable if and only if the M1 here is positive and the M2 has to be smaller than n plus 1. Okay, that's the condition. If this is not met, then it won't be tiled. You won't be able to make it, okay? It looks like it's a complicated matter. You have to start doing that. But in fact, when you use the corresponding non-intersecting paths, it's very easy. It's a very easy to show that. Now, throughout, assume that this kappa is positive. That is to say that this side here is larger than n. The situation is slightly different when this side is shorter than this. But that's a different story. So let me not talk about that now. So the weights, that number A, so on the weights I put the vertical dominoes have weight A, and the horizontal dominoes have weight 1. Okay, that's what I'm doing. And then is the usual formula is the probability on the tilings is such that the probability of a domino tiling T is A to the power of the number of vertical dominoes in T divided by all possible configurations. Okay, that's a probability. And so the goal is to study the random process which kernel K red, because we will see red dots appearing everywhere. So I call it K red. Okay. So this is now a picture that I want to look at, and I want to explain a bit what's going on. So first of all, when you put those tiles, I repeated here those 4 types of tiles with the heights, okay? The first thing that you observe is that on the side here, the heights are specified. You have no choice, because look at this, for instance. Here, what can you do? You can put a tile like this, or you can put a tile like that. But you see that it's always on the left, it will be h plus 1, h plus 1, h plus 1. So it has to be 0, and then 1, 1, then 2, 2, 3, 3, etc. Okay. So everything is specified on so this specifying those heights, that fixes this boundary for the height, okay? And so on. It's an easy, I mean, you just look at it, it's visual. Now, I'm going to draw 2 lines here, and they are just the lines which pass to the place where you have this indentation here. We have the non-convexity, so here and there, okay? And now it's very easy to see that the difference of height between this point and that point is exactly, in this case, it's, well, it's going to be n minus m2 minus 1, it turns out, okay? So you look at difference of height. So therefore, there are exactly that many dots. I'm sorry. So therefore, there are that many intersections of that line with the level lines. Okay. If you go down 6, you have to cross 6 level lines. There's no other way. Then put a red dot in the middle of the tile where the intersection occurs. Okay. So I put a red dot here in the middle here. Here, I mean, this section here, but nevertheless, I put just, it's nicer to look at, you put the red dot in the middle. So here you have 1, 2, 3, 4, 5, and 6. Now you keep doing that. I got a little impatient, keep doing that. You find exactly 6 dots each time, okay? For instance, here you count again, there's 1, 2, 3, 4, 5, and 6. All the way here you also 1, 2, 3, 4, 5, and 6. You find 6 dots. As soon as you leave that strip, okay, then the number increases. Okay, it increases by 1 each time. Okay, so the random point process, which we like to study, is the process of these red dots on these parallel lines. That's really what we want to do, okay? Now, the problem is that because of the fact that when you start on one side, it goes down, the number of dots, and then it stabilizes, and then it goes up again. That makes it hard to study as such, so you have to find another trick to get your hands on the kernel. Okay, that's what I want to explain. And in fact, that's what I'm going to explain by means of pictures, okay? So the mathematics is that along all these parallel lines here going to the black squares, you always have the same number of dots, which is n minus m2 minus 1. And that's a number which we call R, and then the width of that strip is rho. That's to say there are rho plus 1 lines where you have that precise number of dots, and then beyond that it goes up by 1 on either side. Yes?
And the configuration of dots uniquely defines tiling.
Yes,
Yeah.
that's right, yeah. It's, yeah, exactly. It uniquely defines a tiling, that's right. So it's the same information, okay? So so that means it's a random surface, and you have those level lines, and then so it's the point process of these red dots, which we want to study. Then I think I said essentially everything. So in this situation, the n is equal to 8 here. The M1 is 10 here, the M2 is 3, and the kappa was 2, I believe. I mean, yes. Yeah, it's the difference between N and M1, which is 2. So the kappa in question was 2. So let me move to the next slide. Yes, so you can express the width of the strip and the number of dots in that strip. You can express them exactly in terms of these M and N, etc., etc. Okay, they are exact formulas. So let me. Oh yeah, Sunil also made a simulation of the picture which you saw a while ago for these 2 Aztec diamonds. And he drew, in fact, the level lines here, okay? So the level line, we might just have a look at the previous picture. You see those level lines here, they start here, they end up on that side, and then you have another set of level lines here, and here you see that some of them go here, and then some of them go down here, okay? And you see exactly this phenomenon if you analyze that Sunil's picture. That's exactly what you see. I mean, all the ones which start here, they end up there, and then you have these ones. Some of them end up there, and some of them go down here. Okay. So you see again the 2 sort of Arctic circles, and you see that there's something going on here. And I say that's what we are interested in. Yes. Now, in order to study, as I said a moment ago, we are not able to get our hands on a kernel for that configuration because of these varying numbers of dots per line. It's a complicated point process. If it were go down monotonously, it would be possible, but we were not able to see anything. So now there's a trick, is to look at the dual path. And the dual paths are exactly, you might say, it's a dual of this configuration here. So here, what was tilted like that, you make it flat. What was flat, you make it tilted. And this is, well, you take the dual of that, and that amounts to, in fact, drawing a green line going from, a half height to another, to the same half height, etc., etc. Okay, and then, by the way, these were the dots, because you see, we looked at oblique lines like this, which were intersecting those tiles. So that means you see this, you will intersect this level line here, you will intersect this level line there, but you will not intersect that one, because your line is tilted like that, okay? But here it's now the opposite. I'm going to look at not the lines tilted like this, but I will take them perpendicular, tilted like that, okay? And then I will see, what will I see? I will see those tiles here and those tiles, but not that one, because that's going to be parallel to that line. So I put a green dot in the middle. And in fact, the next slide is, now if you do that, I kept here the red path, and I also draw the green path. And you see that every square is visited by either one, either red or green. So that's the duality. And So let me now, the next slide is I remove all the red, forget about all the red, and that's the situation which I find. Now, what's the advantage of this configuration? The advantage is that I have, first of all, the departure, the start point, the points are contiguous, okay? Those 3 points are next to each other, and you end up exactly here at 3 contiguous points. And then you have those pairs going. So also you see that if you look at those oblique lines, the ones which are perpendicular to the other ones, you look at those oblique lines, you see if you follow any such line, you will intersect that green pairs in one place. So you put a green dot here, and a green dot there, okay, etc. So that's now your new random point process, and now we want to write down, we wish to write down a kernel for this situation. But the big advantage here, unlike before where you had red pairs which are leaving, say, from here and then from down here, so they are not contiguous, so everything is complicated, okay? But now there's a nice formula which in fact expresses the kernel for the red pairs, red dots, in terms of the kernel of the green dots, because it is duality. And that formula is given by, I have to specify some coordinates, maybe it doesn't matter. I mean, we'll have 2 sets of coordinates, C and eta, and another set which will be S and Y that direction, but it doesn't matter really. So now I'm going to write down the kernel for the green pairs, and it's in fact fairly standard now by now how you deal with that. So you find the following formula that it is you have such a term. I will tell you in a moment what the PS1 S2 is, plus another term which has a double integral representation. Is given by in the coordinates S1, Y1, which you saw in the previous slide, but it doesn't, detail don't matter. You find, in fact, the double integral of certain transition functions times the ratio of 2 tuplets determinants, okay? The ratio of 2 tuplets determinants for the symbols psi 0 to n plus 1 times some rational function, and that psi 0 to n plus 1. Okay, so that's my tuplets determinant here, but there is something unpleasant. There's something unpleasant because if I look at psi S1 for S2 equal to 2n plus 1, there are certain integers, they are transition functions. They look like z to the kappa, which, remember, z to the kappa was the difference between that side m1 and n, times a certain good function, okay? And of course that makes for a tuplets determinant which is singular, okay? So I somehow have to deal with that, okay? So how do I deal with that? It's then based on a, I would say, key lemma. That's really what enabled us to actually do the whole analysis, is that the tuplets determinant of zeta to the plus or minus kappa, it doesn't matter, f of zeta, is equal to the integral. So what you do, the zeta to the kappa, you actually, you actually blow it up. You blow it up and you integrate, okay? So I blow it up by replacing the zeta to the kappa by a polynomial, p lambda of zeta is equal to the product of lambda I minus zeta, okay? And I then integrate with regard to about a circle of radius r. It's a multiple integral, k-fold integral of this tuplets determinant. But so that means that by introducing those artificial variables lambda j and by integrating them out, you avoid that problem. But of course you have to carry that integral, you have to carry it around all the way, so which leads to a lot of complications, okay? And then there's a standard thing also, I mean, the formula of Cauchy-Geronimo-Borodino-Kunkov is that you can express this tupless determinant as a Fredholm determinant of a certain kernel, okay? Certain kernel kappa, which I don't want to write down. It's a fairly standard procedure, but of course you still have this lambda j integration here, okay? This I will call that the Borodino-Kunkov kernel that comes back all the time, but I don't want to write it down. I mean, that's details.
It's the kernel for the remainder term, right?
I beg your pardon?
It's kernel for the remainder term. They express tupless determinants through Fredholm determinants.
Yes, exactly. And then, of course, you have to keep the integration. So there are two things, okay? Yeah. So now, as I said, we are able, so now we were able to compute the kernel for the green dots. Okay, that's the formula which I wrote down for you with the integration and the Fredholm determinant of the kernel. And I want to transform this into this actually I call it the blue kernel. And the blue kernel goes with the same red path as before, but I draw lines like this because here also the lines are like this. Okay, so the random point process now is not the random point process which we really need, which is the lines like this, but the lines like that. I mean, that's life. I mean, you go from there to there, and that's life. Okay, so that means that you see some blue dots. Maybe they're not very visible, but if you take up those lines, you see those blue dots here, blue dots there, etc., etc. And they are different. They are different from the red dots, and I will show in the next slide. I will show it to you why they are different. So now there's a rather standard formula. When you have this duality, you can express the kernel for these blue dots like this as the indicator factor u1 equal to u2 minus the green kernel. And that is, the n is just take any level here. I mean, the n now happens to be its n, but it has nothing to do with that length. You take any fixed level here, and then you look at the correlation at two different places that gives you this, okay? So that's also standard. Of course, you have to be able to get this thing in a form, again, that you can work with, okay? So there's quite a bit of complication due to that integration. But anyway, that works. And you can then extend, that's also standard, you can extend this to, you know, before in the previous slide, we had put a fixed level, a fixed line, n and n here, and now you can extend this to S1 and S2. That's also a fairly general procedure. And that gives you the blue kernel. I'm not done because I now have to get the red kernel. I mean, that is to say the intersection of the level line with those directions. So there's another step, is to go from K blue to K red. Okay, so I drew here the blue dots along those lines, and I have to go from there to there. Okay. Now there's another, I would say, miracle here, is that I mean, everyone knows that this configuration has an interpretation in terms of diamond models. The diamond model is produced by putting a blue dot, it's in fact the dual of this, there's too many, by putting, say, a blue dot in the middle of a blue square and a white circle in the middle of a white square, okay? That's the diamond model, and then you put arrows in all you have four different, if you take an arbitrary blue square here, there are four ways you can put a tie like this, a tie like that, or like that. So you have four arrows leaving from that point. So in this way you have a diamond model. Then you can write down the adjacency matrix for that. That's called the Castelline matrix. I mean, that's very old, it goes back to the 40s. And now the miracle is that, yes, I still wanted to show that, you know, these are these are here, these are the blue dots here, because you intersect them with lines like this that you don't see, but you see this, because you will intersect that lines, you have a blue dot. But I'm interested in the other ones, with lines like this, so that means I have to intersect that with lines like that. That gives you a dot here, which is actually the same as that one, but you get this gets transformed into this. So you will see this one, and this you won't see with the. So that's the difficulty here. Now, yeah, let me not go into the detail, but when you write down this Castelline matrix, the miracle is that the inverse Castelline matrix, which no one in the world would like to compute, the inverse of that huge matrix. It's a fairly sparse matrix, but still it would be very, very complicated. But in fact, it turns out to be, modulo some change, slightly translations, it turns out to be the blue kernel, okay? So that's a very remarkable fact. And in fact, it's not so hard to prove, because what you do, I mean, you take the Castelline matrix and you multiply with the K blue, but the Castelline matrix is basically translating to the left, one step to the right, one step up or down. So it's a difference equation, you might say, for this blue kernel, which you have explicitly. Of course, it's work, it's hard work, you have to check it, especially the work lies on the boundaries, where you have all kind of things happening, you know, you have this indentation and so on, but it's labor. So you can therefore deduce the red kernel from, when you have the Castelline matrix, basically you can compute any probability, because that's the full story. But then you can deduce the red kernel, you can deduce it. So we know from this, we know the Castelline matrix, and then you deduce the red kernel from the Castelline matrix, okay? I mean, it uses, again, a rather standard theorem, which is, whether is it due to Recanzone, but maybe it was known before, maybe that was known already by Castelline, I'm not sure. So now let me do scaling. So far, it's a lot of algebra, and so the scaling now. Yes, I still have 20 minutes. So I'm going to be interested in. Remember, I'm going to be interested in what happens in the middle here. Okay, basically around this point here. So that means that this coordinate is going to be approximately n. You know, this was the eta coordinate. It's going to be n here in the middle, and the xi coordinate here, it will be, and this is about 2n here. So that means I'm going to scale about, and also I see that the n, I'm going to be interested in what happens here. It's certainly in between the strip in question. There is a strip formed by those two lines which are near the indentation. Anyway, so then this is the scaling. This A, remember this A is a discrepancy of probability between horizontal and vertical. That's A scaled like this. The xi variables are scaled about 2n. This is now a discrete variable xi, so the xi will remain a discrete variable. The eta I scale like n plus has a square root 2n scaling, okay? That means in that direction it is square root of 2n. It's discrete in that direction, but it's square root of 2n scaling in that direction. And so if you put that in your red kernel here, you will find there are certain things which come out, but they are conjugation. You know, a kernel, you always can conjugate by things, so you can remove these things, they don't matter. And you find a new kernel, which I will call L red. I mean, it's just after putting in all that stuff, I want to let n go to infinity, okay? And go to infinity, because if n goes to infinity, the m1 and m2 go to infinity, but the kappa, the rho, and the r, so these numbers here, I mean the width of the strip and the number of dots on the lines in the strip, that remains fixed, okay? You don't move them, but all the rest goes out to infinity. Just for convenience, let me put n equal to 1 over t square, but this is the precise scaling. So, okay, I don't want to say much about all these expressions. There are lots of integrations involved. There are millions of contours floating around, so you have to be super careful. This is some sort of Heaviside function here. These expressions are double integrals of certain expressions. This A and B also are double integrals. This is your Bordino-Kunkov kernel. You take the resolvent of it. The L, remember the lambda integration? That is still there. You carry it around all over. The lambda integration is this. It's the integration with regard to this measure of the Fredholm determinant of the k lambda times a function. And no. So I cannot explain to you in 2 minutes what you do. I mean, there's lots of little tricks that you use. I mean, it just gives you. Let me give you an example. The second one, you take 1 minus a plus a of w times b tensor with b of z. You integrate. This is independent of w and z. You integrate those two things. Then, in fact, you can pull it through. You can pull it through. You can integrate with regard to f and the b with regard to g, but you pay a price for that. And the price that you pay is that you have to add this thing, but it's not so bad. It's quite pleasant. I mean, things like that. You also use stuff on Schur polynomials, expansions of symmetric functions in terms of Schur polynomials, etc., etc. Yes. So the limiting kernel now. So if you are, I mean, the work isn't finished because then you get an expression and everything blows up. So that means you have to massage this expression and get something which you can deal with, of which you can take limits, okay? And I don't want to go into that. And once you have this expression, you can then take the limit when t goes to 0. That means when n goes to infinity, and you find the so-called discrete technode kernel, which I will show you in the next slide. That's the discrete technode kernel. I mean, some of you have seen it in a different context. It's a sum of, this is a Heaviside function. It's a sum of four double integrals. This is the integral over a circle about 0. This is an integral about an upward integral of a line which lies to the right of that circle. And here you get mix of things. This is again gamma naught and lambda 0 plus, and this is L0 plus up L0 plus. This is gamma naught. And you sort of have these Gaussians here appearing all over the place, all a little different, times some functions here, which we call theta r, times those functions here, okay? Yes?
Is the reason for the Gaussian the fact that you have sort of two GUE processes sort of appearing?
Yes, yeah, it is. Absolutely, it's certainly very closely related to GUE, exactly. Yeah, so absolutely. And in fact, the last slide I will show you deals with that question. So, but it's not all of it, because you now have those functions theta r, and those theta r, they are r-fold integrals. Remember, r was a number of dots on those lines within that strip, okay? So let me tell you what these theta r's are. I mean, they are r-fold integral, you see them, okay? They are in fact, they are basically GUE. I mean, they are GUE averages of certain rational functions here, but with a pole here, and the pole depends on the width of the strip, on that width row, okay? So all these things come in, yes. Now, you might say, well, this is, you can't do anything with it, it's a big formula. But in fact, if I take 2 points, which are, say, within the strip, 2 points, x1, y1, and x2, y2 within the strip, already 2 of the integrals disappear. If I take 2 points outside the strip, they also disappear. 2 other integrals disappear. It is just what's more complicated when you take 1 point within the strip and 1 point outside the strip. I mean, then, in fact, nothing disappears. Now, let me, in the remaining few minutes, let me just, yes, the theta. Now, let me look at it, let me say very, very briefly, let me look at another problem, which is the lossless tilings of non-convex polygons. I will not go into any detail, but I mean, this is a non-convex polygon, okay? You see this, I mean, it's a hexagon, basically, hexagon, but you have 2 indentations here, okay? And this is a tiling, which it's a very nice picture, which was made by a former student of TAM, Antoine Doran. And then, actually, it turns out that if you do all the calculations, you go to all the calculations, but the geometry and the analysis is very different. But you actually find exactly the same 4 double integrals as before. Okay, so that means that's you might say that the kernel is fairly universal in the sense that you find in 2 entirely different situations. There's no direct map between one or the other, but the thing is, in the end, after all the effort, you find exactly the same kernel. And I like to show you some simulation, which also made very nice pictures made by Antoine. You take this is your this is your hexagon here. You have the 2 indentations. What you find is, in fact, something like that. You have a Arctic ellipse here. There you have an Arctic ellipse here. And then you have sort of paths which are going from one ellipse to the other. You sort of have filaments, okay? And the number of these filaments is exactly equal to that number R, which I mentioned before, okay? So what we are interested in, for instance, is to find out what would be the statistics. Suppose I take a line like this, what would be the statistics of those filaments along that line, of the intersection of those filaments with that line, okay? And yeah, that's a magnification of that. I mean, you see very clearly, you can actually, the combinatorics comes out perfectly in that picture. But you find the following fact is that if you look at the number of intersections of those lines with those filaments, you find that that probability is equal to a certain expression d, dx. If I take 2 points, t1, tau1, and tau2, which are inside the strip, or 2 points outside the strip, then you find that same function d, like this, times the volume of a certain polytope. So that means that shows that this system has the Gibbs property. And then I have to say something about those d's, what they are. They are the following expressions. I mean, the same formula as before. They are the following expressions. They are the product of a Van der Monde determinant times Gaussian. So it looks very much like GOE, but this is not exactly a Van der Monde determinant. It's something slightly different. So this is outside the strip, and inside the strip there's no Gaussian, but it's a product of 2 such expressions. So I want to give you a little idea of what this really is here. So those delta are things like that. They are determinants of something which tries to be Van der Monde, but then at some point there's a function phi which appears, okay? Function phi which appears. And in the other case, when you are inside the strip, then in fact it's all is phi-like. Then I have to tell you what the phi is. The phi is this integral. The phi is this integral, which we know is equal to this integral for k positive times some Gaussian, and it's equal to Hermite polynomials for k smaller than -1. Okay, so that means you have those kind of Van der Mondes, which are, it's partially Van der Monde. You get a piece which is given by this integral here, and another piece is given by those Hermite polynomials times some Gaussian. Okay, so that's really what the statistics is. Now you might say, why are we interested in knowing that, except that, well, it's a universal kernel. And the reason is the following. We have, and that's work in progress, we have very strong suspicion that absolutely everything about tilings can be deduced as scaling limit of that kernel. Okay, so that means the Dyson-Brownian motion, the tech-node kernel, which I didn't mention here, the cusp airy kernel, all these are appropriate limits of the discrete tech-node kernel. Now, there's a forthcoming paper by Kari Astala and Erik Duse. I mean, Erik Duse is Swedish, Astala is Finnish at Helsinki, and I haven't seen the paper, but I've heard about it. They show that for a reasonable class of diamond models, you can only have two kinds of singularities. I should say three kinds of singularities, that the Arctic circle, the Arctic shape, that it touches the boundary. You can have a cusp, or you can have a tech node. That's what they show. So therefore, if this program, so that's where Kurt and Mark wanted to pursue this project. So if we can show all these arrows here, then in fact we have really a master kernel for all these problems. I mean, that's in a way, you might say that's the end of the story, okay? Thank you very much. And I even finished 5 minutes early.
So we thank Professor Pierre Van Moerbeke for his beautiful lecture and for finishing so nicely on time. So we have time for questions.
Yes.
Yes.
And complaints, of course. Time for complaints. Okay.
This techno thing. The techno that you were mentioning. There is another tech node of Daudz and Borodin, right? That's different than the situation you're describing.
No, I mean, the thing is, the tech node is, you see, maybe I can somewhat explain this by means of that picture here. This is a good picture. See, if you somehow push these two pictures together, then in fact you will get you could imagine that you get two Arctic circles which just merely touch. And
so it is two cusps that come together at infinity.
Yeah, that's right. And then if you push it further, you will get two cusps. But a cusp, in this case, we know there are two kinds of cusps. I mean, a cusp is a cusp, but there are two kinds of phenomena. You can have, maybe I should draw this briefly. I mean, the first kind of cusp is the following, where this is frozen. This is frozen, okay, and this is stochastic. And here we have the so-called PSC process, okay, which was actually introduced by Craig and Harold many years ago. This is the PSC process here. But you can have another kind of cusp. It's still the same geometrical cusp, where you have a line here. This is frozen blue, say, and this is frozen red, okay? And the line, there's a line here, the boundary between blue and red goes straight to that cusp. And that is a different statistics here from this. Very, very, very different. This is PSC-like, this is more Airy-like. But it involves quite a few. I mean, that was described by Duse and Kurt, and then yes, Metcalf. That's right, exactly. Yes, yes. So we expect very strongly, that's ongoing work, I will tell you about that next time. It's ongoing work, we expect very strongly that you can get this Piercy and you can get this guy here also. That's what we expect. Okay.
Further questions?
So the transition from the discrete to the continuous tech node, is this still unknown, or is it? Do you know how to
From
do it?
discrete to tech node, that's ongoing
from your
work.
formulas, right?
Sorry?
From your formulas that you have.
Yes.
So that can be done.
Yes, I say that's ongoing work. Next time I'll tell you.
Okay.
Okay, and while we are
if there is a next time.
while we're looking forward to next time, we thank Professor Moerbeke again.